The objective of this video is to show you how to address three important attributes of a linear regression analysis. The problem we're going to use from homework 11.3 through 11.5 is as follows. An engineer is interested in studying the rate at which spilled volatile liquid will spread across a surface for a defined geometry. She calculates the mass in pounds of a 50-gallon methanol spill after a period ranging from 0 to 60 minutes. The results are summarized in the table below. So what I did is I just typed in the X column, both labels and numbers, for time and mass. Time is on the X-axis, mass is on the Y-axis. We're going to solve for three different items. One, the coefficient of determination. Part two, solve for the correlation coefficient. And three, to calculate a 95% confidence interval for the slope of the least squares regression line. The way we're going to perform this is much like what we did in the last video. We're going to hit data analysis. We're going to hit regression. Okay. I'm going to clear these fields. And we're going to input for the Y range. We're going to highlight this column. And the X-axis, we're going to highlight this column. Here, because we're being asked to calculate a confidence interval for the slope of the line, we are going to click confidence level. 95% is the default. Our output range, we're going to highlight and put down here. And I'm going to click OK. Okay. Now, before we start to analyze this, I'll note that the chart depicts a negative slope. Okay, so if we just pick up where we left off before, these would be our parameters for the least squares regression line, and I'll just note that our slope indeed is a negative, so that does check with this scatter plot with the line through it, with the least squares regression line through it. Question one, solve for the coefficient of determination. Okay, well, for a linear regression problem, R squared is, let me do this again. This is the coefficient of determination. And what this provides us, or what this tells us, 72% of the variation in the values of mass are explained by the explanatory variable time. I would reference you to the notes for further explanation. So your answer for part one, you would plug in 0.724. For part two, which happens to be a question in homework 11.2, that is multiple R, okay, and this is the correlation coefficient, and that tells us or gives us an indication of the degree of linearity between X and Y. And so in both of these, both multiple R, or the correlation coefficient, and R squared, the coefficient of determination, the closer these numbers are to 1 for a correlation coefficient means the tighter that the linear relationship is between time and mass. And as this number approaches 1, would indicate that time is by far the largest variable that explains the variation in mass. As a rule of thumb, you want to make sure if you're going to use this analysis for prediction purposes, you want this R-squared to be at least 0.6. 0.85 would indicate a very tight variation. The last thing we want to do is we want to know if our slope, okay, if this negative 0.8 or negative 0.089 is a good predictor of the y variable or the response variable mass. And so what you do is you come down, and there's a couple things you can look at. First of all, you can look at your confidence interval of the slope, and you will see for 95% both values are negative, which does not include 0, and therefore you would reject a null hypothesis of beta 1 equaling 0, and in favor of an alternative hypothesis that says there is significant or sufficient evidence to say that time is a good predictor of mass. The other thing you can do is you can look at the p-value, which is 0.007, and it is less than 0.05, which also tells you you can reject a null hypothesis that beta equals 0. So with both checks, we have determined that beta 1 is not equal to 0, and it is a good predictor for the response variable y, which is mass. That concludes this video.